Assalamu alaikum, brothers and sisters. Welcome to the journey of quest where we quench your thirst of knowledge. Unearthing the past. A glimpse into Earth's history. Imagine, if you will, standing amidst the ruins of Pompeii, a Roman city frozen in time by the eruption of Mount Vesuvius. The layers of ash and debris entombed the city, preserving a snapshot of life in 79 AD. This dramatic event serves as a powerful reminder of how the Earth's history is etched in its layers. Just as archaeologists carefully excavate Pompeii to unravel its secrets, geologists delve into the Earth's strata to decipher its long and complex history. This process of deciphering the Earth's history through its layers is called stratigraphy. It's a fundamental discipline in geology that allows us to piece together the story of our planet from its formation billions of years ago to the present day. By understanding the principles of stratigraphy, we can unlock the secrets hidden within the Earth's crust. These layers, much like the pages of a history book, tell a tale of changing climates, evolving life forms, and dramatic geological events. They offer a glimpse into the past, revealing the forces that have shaped our world and the life it sustains. What is stratigraphy? Stratigraphy is the study of rock layers, or strata, and their relationships in time and space. It's a branch of geology that focuses on the interpretation of sedimentary rocks, which are formed from the accumulation of sediments over time. These sediments can include sand, mud, and organic matter, which are transported by wind, water, or ice and eventually settle in layers. These layers, when compacted and cemented, form sedimentary rocks. The process of layering is continuous, with new sediments constantly being deposited on top of older ones. This results in a vertical sequence of layers, with the oldest at the bottom and the youngest at the top. This simple principle forms the basis of stratigraphic analysis. By studying these layers, geologists can reconstruct the order of events that occurred in the Earth's past. They can identify periods of mountain building, sea level changes, and even the evolution and extinction of species. The law of superposition, layers of time. One of the fundamental principles of stratigraphy is the law of superposition. This law states that in an undisturbed sequence of sedimentary rocks, the oldest layers are found at the bottom, and the youngest layers are found at the top. This principle is based on the simple observation that sediments accumulate over time, with newer layers being deposited on top of older ones. Imagine a stack of newspapers. The oldest newspaper is at the bottom of the stack, and the newest is at the top. Similarly, in a sequence of sedimentary rocks, the oldest layer is at the bottom, and the youngest is at the top. This principle allows geologists to establish a relative chronology of events, determining which layers formed first, second, third, and so on. The law of superposition is a powerful tool for unraveling Earth's history. It provides a framework for understanding the sequence of events that have shaped our planet over millions of years. The principle of original horizontality, flat Earth. Another key principle in stratigraphy is the principle of original horizontality. This principle states that layers of sediment are originally deposited in a horizontal position. In other words, when sediments settle out of water or air, they tend to form flat horizontal layers. This is because gravity pulls the sediments downwards, creating a level surface. Of course, we know that the Earth's surface is not perfectly flat. Mountains, valleys, and other geological features demonstrate that the Earth's crust has been deformed over time. However, the principle of original horizontality still holds true for the initial deposition of sediments. If we find sedimentary rock layers that are tilted or folded, we can infer that they were originally deposited horizontally and then later deformed by tectonic forces. This principle helps geologists understand the processes that have shaped the Earth's surface. It allows them to distinguish between original sedimentary structures and those that have been altered by subsequent geological events. Section 5. The principle of cross-cutting relationships, disruptions in time. The principle of cross-cutting relationships states that any geological feature that cuts across another feature must be younger than the feature it cuts. In other words, if a fault cuts through a layer of sedimentary rock, the fault must have formed after the sedimentary rock was deposited. This principle is based on the simple logic that something cannot cut through something else that doesn't yet exist. This principle is crucial for understanding the relative ages of geological events. For example, if a volcanic dike cuts through a sequence of sedimentary layers, we know that the dike is younger than the sedimentary layers. This allows us to reconstruct the order of events in a particular location, piecing together the geological history of the area. The principle of cross-cutting relationships is a powerful tool for deciphering the complexities of Earth's history. It allows us to disentangle the web of geological events, identifying the sequence of processes that have shaped our planet. Section 6. Reading the Rock Record, Unraveling Past Environments. Sedimentary rocks are not only a record of time but also a record of past environments. The type of sediment that accumulates in a particular location reflects the environmental conditions that prevailed at the time of deposition. For example, fine-grained mudstones suggest calm, deep-water environments, while coarse-grained sandstones indicate high-energy environments such as beaches or rivers. By studying the characteristics of sedimentary rocks, geologists can reconstruct ancient environments. They can determine factors such as water depth, current velocity, and even the climate of a particular region. Fossil evidence found within sedimentary rocks provides further insights into past ecosystems, revealing the types of organisms that inhabited these environments. This ability to reconstruct past environments is crucial for understanding Earth's history. It allows us to track changes in climate over time, identify periods of glaciation, and even predict the future impacts of climate change. Fossils, the preserved remains of ancient organisms, are often found within sedimentary rocks. These fossils provide a direct record of life's evolution over millions of years. By studying the distribution of fossils in different rock layers, paleontologists can trace the emergence, diversification, and extinction of species over time. The fossil record reveals a remarkable story of life's journey on Earth. It shows how organisms have adapted to changing environments, evolving new traits, and giving rise to new lineages. Stratigraphy provides the framework for understanding this evolutionary history, allowing us to place fossils in their proper chronological context. Through stratigraphic analysis, we can track the rise and fall of dinosaurs, the emergence of mammals, and the evolution of our own species, Homo sapiens. Stratigraphy underscores the dynamic nature of our planet. The Earth's crust is constantly in motion, driven by tectonic forces that cause continents to drift, mountains to rise, and oceans to form and disappear. These processes leave their mark on the rock record, creating complex patterns of folding, faulting, and uplift. By studying these patterns, geologists can reconstruct the history of Earth's tectonic plates, piecing together the movements of continents over millions of years. They can identify ancient collision zones where continents have collided to form mountain ranges, and rifting zones where continents have pulled apart to create new ocean basins. Stratigraphy provides a window into the dynamic processes that have shaped our planet, revealing a story of constant change and evolution. Stratigraphy is not just an academic pursuit. It has practical applications in various fields, including resource exploration, environmental management, and hazard mitigation. For example, stratigraphic principles are used to locate oil and gas reserves, as these resources are often trapped within porous sedimentary rocks. Stratigraphy also plays a crucial role in understanding groundwater resources, as the distribution of aquifers is controlled by the layering of sedimentary rocks. In addition, stratigraphic analysis is used to assess the risk of natural hazards, such as landslides and earthquakes, as these events are often associated with specific geological formations. By understanding the principles of stratigraphy, we can make more informed decisions about resource management, environmental protection, and public safety. Stratigraphy is a powerful tool for unlocking the secrets of Earth's history. It allows us to travel back in time, exploring ancient environments, tracing the evolution of life, and understanding the dynamic processes that have shaped our planet. By studying the layers of sedimentary rock, we can piece together the story of Earth's long and complex journey. The principles of stratigraphy provide a framework for understanding the order of events, the relative ages of geological features, and the environmental conditions that prevailed in the past. This knowledge is not only fascinating but also essential for addressing modern challenges related to resource management, environmental protection, and hazard mitigation. Stratigraphy reminds us that the Earth is a dynamic and ever-changing planet, with a rich and fascinating history waiting to be discovered. Thanks for watching us share our videos. Subscribe our YouTube channel and press the bell icon and stay curious for new uploads.